Okay, part 2, starting at number 7. Sketch the graph of the quadratic function. The graph of a quadratic function is a parabola. This parabola is in general form. In order to graph a parabola, one of the first things we always have found is the vertex. There were a couple of ways that were shown in class of finding the vertex. One of the ways that was done most often is to complete the square to write general form of a quadratic function into standard or vertex form of a quadratic function. So that's the method I'm going to choose. It starts by subtracting 4, moving the constant. That's going to result in y minus 4 on the left. Now the quadratic expression on the right has a leading coefficient of 3, so that needs to be factored out before completing the square. That leaves you with x squared plus 2x. And now we complete this trinomial by using the formula. Okay, the number that completes that is half of b raised to the second power. And it's not half of the original b, 6, it's half of this b now that you factored out the 3, so half of 2 is 1, 1 squared is 1. So we're adding a 1 inside the parenthesis, but outside the parenthesis is a 3, so 3 times 1 is really a 3 that we've added, so we need to add a 3 to the left side, which results in y minus 1. Now the x squared plus 2x plus 1 factors into x plus 1 squared. Now if we add the 1 back over to the right to isolate y, we have y equals 3 times x plus 1 squared plus 1. Now the vertex is then negative 1, comma 1. The reason for that, remember, inside the function is a horizontal change, and it's also the opposite. Plus 1 moves the vertex to the left 1 unit. The plus 1 on the outside moves it up 1. That's why the vertex has been moved to negative 1, positive 1. Now we know the vertex is negative 1, comma 1. We need to locate some other points on the graph, so we can choose some x values now to plug in, keeping them relatively close to where the vertex is at negative 1. So if we let x equals 0, y is going to be 4. And then if we use symmetry, a parabola is symmetric, so that point can be reflected to over there. Okay, sketch the graph of a polynomial function. The graph of a polynomial function, a couple of key things to remember. First of all, it's smooth and it's continuous. Smooth means there's no corners. Like a V-shaped absolute value graph, that wouldn't be considered smooth. Continuous means there's no gaps or holes, like the piecewise function we just graphed back in part 1. Smooth and continuous. And the reason I'm stating this is we graph a lot of graphs in 1050 that have asymptotes and gaps and different pieces everywhere. The polynomial function is smooth, connected, continuous. It's just something to remember. Okay. The steps that we're taught. Step 1 is to use factors to find zeros and the multiplicity of the zeros. And the multiplicity is important because there's two types of zeros. There's a 0 where the function crosses through at that point, and there's a 0 where the function bounces off the x-axis at that point. And that's determined by the multiplicity. Okay? So if we want to finish this step, looking at the factors, a factor of x plus 1 is going to produce a 0 of x equals negative 1. And since this factor appears 3 times, according to its degree, that has a multiplicity of 3, which means the graph is going to cross through at that point. Now the other factor, x minus 2, produces a 0 of x equals 2. That has a multiplicity 2 according to its degree, so at this point f of x is going to bounce off the function or the x-axis. Okay, now step 2 is to find the y-intercept. You let x equal 0. always, for any function, if x equals 0, you plug 0 into the function. 0 plus 1 is 1, 1 to the third is 1, 0 minus 2 is negative 2, but negative 2 squared is 4. 1 times 4 is 4. So if x equals 0, y equals 4. Now the third step is to use the degree of the polynomial to determine the end behavior. All polynomial functions of any degree are going to have end behavior that's either like a parabola, where both ends, like a parabola here, both ends are going up in the same direction, or they're going to have opposite end behaviors that behave like an x to the third graph, kind of like this one. And it's dependent on the degree. If it's an even degree polynomial, its end behavior is going to be the same as x squared. If it's an odd degree polynomial, the end behavior is going to be the same as x to the third. Now, you can add up the multiplicities or add up the exponents when it's in factored form to determine the degree, but this is degree 5. Which means its end behavior, if you look at a little snapshot of the graph, it's going to have this sort of end behavior like this, opposite, traveling in opposite directions. Okay. Now, the graph is coming from down here. We know it has to cross through the x-axis at that 0, and it goes to our y-intercept of 4, but now we got to decide, does it turn straight down and come to this 0, or does it continue to go up a little bit and come down? That's what's called a local maximum. Okay. There's kind of a gap here between 0 and that, between x equals 0 here and x equals 2, so we could figure out the value of the graph at 1 by plugging in a 1 for x. Turns out that if x is 1, y is equal to 8 up here somewhere. So the graph goes all the way up to 8 before it turns down towards this 0. It bounces off that 0 because of the multiplicity of 2. And there's the graph. Okay. Question 9. We spent quite a bit of time talking about questions like this. This is from section 4.4, 4.5 out of your book. It's kind of a big deal for 1050, being able to factor a polynomial and finding its zero. So what we did first is made a list. Use rational zeros theorem. Rational zeros theorem gives you a list of possible rational zeros that you can test using synthetic division. That's the p's and q's. P divided by q. Factors of 18 are p. Factors of the leading coefficient here are q. So p divided by q is going to be a list of plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. Now step 2 is to test using synthetic division, and if you get a remainder of 0, that means you found a 0 to the polynomial. A remainder of 0 means that the factor you chose divides into the polynomial evenly. So I'm going to start by testing 1. Testing it using synthetic division. Using the coefficients of the polynomial, and there are no missing pieces. There's x to the 4th, x to the 3rd, x squared, x to the 1, and then our constant. So no missing pieces. We don't need a placeholder of 0. Now perform the synthetic division. And we have a remainder of 0, which is what we wanted. So that means that x equals 1 is a 0. That also means that x minus 1 is a factor, and we'll have to keep that in mind for part B. X minus 1 is a factor. Now if x minus 1 is a factor and we've divided it out of p of x, this is the polynomial that will be remaining, x to the third plus 2x squared plus 9x plus 18. Any remaining factor of p of x would also be a factor of this smaller polynomial. So we can continue to test from this list of possible rational zeros on this smaller polynomial rather than the original one. And we've found another zero, x equals -2. And what's remaining now, we started with an x to the fourth and we found two zeros, which has resulted in an x to the second power, or an x squared polynomial here, second degree. So if we factor p of x at this point, with the two factors we have, we'd have x minus 1 times x plus 2, and then this right here gives us a factor of x squared plus 9. Now it's not fully factored until all the factors are linear. This factor here is quadratic. Once you get it down to a quadratic factor, you no longer need to do synthetic division, because you can find the zeros of a quadratic factor either by factoring or by using the quadratic formula, or in this special case, which doesn't happen very often, since there's no linear term, there's just a quadratic term and a constant, you can find the zeros by using square roots. So if we take the factor x squared plus 9 and set it equal to 0, and then subtracted 9, and then square root on both sides will leave us with x equals plus or minus 3i. So here are our four zeros, and then we need to find four zeros because p of x began as a fourth degree polynomial. And for part B, now we can write p of x fully factored since we have all four zeros. X minus 1, x plus 2, x minus 3i, and x plus 3i. Okay, number 10, this comes from section 4.6. Commonly one of the sections that is struggled with the most, not for the level of difficulty I think, but just the amount of material that needs to be remembered to complete a problem like this. Start by factoring whatever you can factor. X squared minus 4 factors into x minus 2, x plus 2. Now the domain of a rational function, you have to find exclusions in the domain, because anytime you have a 0 in the denominator, you're going to have an exclusion in the domain. X can't be 2, because 2 minus 2 would turn this factor into 0. X cannot also be -2, because -2 plus 2 would turn this into 0. So those are your two exclusions. X cannot be 2 or -2, and in the graph of a rational function, those exclusions are in the form of vertical asymptotes. X cannot be -2, and x cannot be +2. Those are your vertical asymptotes. Okay, so there's vertical asymptotes. A horizontal asymptote has to do with the degree of the numerator compared to the denominator. There were three different cases we learned. In the case where the numerator is of smaller degree than the denominator, that results in a horizontal asymptote of 0. If the numerator and denominator happen to have equal degree, then the horizontal asymptote would be the ratio of their leading coefficients. If the numerator has a higher degree than the denominator, there is no horizontal asymptote. Now the intercepts, there's x-intercepts and y-intercepts. The x-intercepts can be found by taking the numerator and setting it equal to 0. That's how you find x-intercepts of a rational function. If you take the numerator and set it equal to 0, that's going to give us an x-intercept of 0. Let me do that in a different color. To find y-intercepts, again, you let all the x's equal 0. 0 divided by 0 minus 4. That's 0 divided by -4, which is 0. It's in the same spot as our x-intercept. Now the third step is to figure out where the graph fits into all these different quadrants of the graph that we've broken this up into. And the way that we did this is by using end behavior as x approaches an asymptote, the end behavior of y. So, for example, as x is approaching the asymptote of 2 from the right-hand side or from the positive side, we would say as x approaches 2 from the positive side. What we need to figure out is where is y approaching. Y approaches what? So we can choose a test point on the positive side of, or on the right. Now, positive, I mean the right side. So any test point on the right side, 3 for example, if we plug it into the function, 3 gives us a plus on the top. 3 squared minus 4 gives us another positive number on top. Positive divided by a positive means that if you plug in a 3, you have a positive value somewhere. And the graph has to stay positive. It can't cross below the x-axis because there's no 0 over here. So y approaches positive infinity. The graph is contained in this top corner. Now, on the other side of that asymptote is as x is approaching 2 from the negative direction. This is the negative direction, and x is approaching it. We've got to figure out what's happening with y. So if we choose a test point of 1, for example, 1 gives us a positive number in the numerator, but 1 squared minus 4 results in a negative number. And a positive divided by negative is a negative, so that shows us that y is going to be approaching negative infinity as x is approaching and getting closer to that intercept, or to that asymptote. And then let's do the same end behavior on both sides of this vertical asymptote. So as x is approaching negative 2 from the negative direction here, it's approaching negative 2 from the negative direction, y is approaching, now if we choose an x value of negative 3 as a test point, negative 3 on the numerator results in a negative value. Negative 3 squared minus 4 results in a positive value. Negative divided by positive is negative. So what this is saying, as x is approaching that asymptote from the negative side, y is approaching infinity. And then as x approaches negative 2 from the positive direction, y, if we choose negative 1, for example, as a test point, we get negative on the numerator. Negative 1 squared minus 4 is another negative number. Negative divided by negative is a positive. So as x is approaching negative 2 from the positive side, y is approaching positive infinity. Okay. The graph looks something like that. Now part B is almost the same exact thing as part A. If you factor the denominator, you're going to get x minus 4 times x plus 1. And then you have x minus 1. So that results in vertical asymptotes of positive 4 and negative 1. Since the degree of the numerator is smaller than the degree of the denominator, we have another horizontal asymptote at 0. Now to find the x-intercepts, we set the numerator equal to 0, and we're going to get 1 as an x-intercept. If we find the y-intercept by letting x equal 0, we're going to have negative 1 divided by negative 4 times 1, which is positive 4. Now we need to determine the end behavior. And that's an exercise I'm going to leave up to you. To finish, you can find the answer on the review answer sheet posted on the Canvas website. I think that would be good practice. And this will be the end of part 2 of the review.